What's up? Proof, set theory, and logic. Welcome back. Another fun week. Let's do it. So hopefully the exam went well over the weekend. For the online folks, I know there's a little bit of trouble with the honor lock system. I sent an announcement about that. We'll figure that out in the future. But for everyone in class, how'd it go? All right? Pretty good? Cool. I obviously haven't graded. I've been gone all weekend. So now that I'm back, I will grade it soon, and you'll get it back very soon. Hopefully it went well. Fun. If you recall, last time we were talking about the product of sets. So remember, we had this definition. So we said the Cartesian product of two sets, A and B, denoted by A cross B, A times B, is the set A cross B, which is ordered pairs of elements A and B, such that A is in A and B is in B. Okay. So here we talked a little bit, the last time we talked about this, about how would you possibly encode an ordered set, an ordered pair, and we came up with some ideas for how you might do that. But ultimately, for the moment, you can just assume ordered pairs exist and work the way you think they do. The encoding you happen to choose doesn't effectively matter in terms of how they work, but hopefully, if you recall when we talked about that, it at least convinces you that we don't actually have to introduce some new object called an ordered pair, something that doesn't exist in the lands of sets, but instead that the notation of an ordered pair is a convenience to somehow represent something that we could do with sets should we decide to adopt a particular convention. Okay, so we had ordered pairs, and we started thinking about how we could do things with these. We had a theorem that I believe we were just about to start proving last time, and then we ended. So it said, for any sets A, B, and C, we have the following. 1, A union B, that set, cross C, is equal to A cross C union B cross C. Likewise, we had that A intersect B, that set, cross C, is equal to A cross C intersect B cross C. And finally, we had that A set minus B cross C is equal to A cross C set minus B cross C. That is, everything works as well as you could hope for. The product takes a pair of sets and from it produces a new set. And any of the nice operations that we can do on individual sets distribute effectively through this. That is, we take a union, a way of taking two sets and making a new set, and then we cross it with something to make a new set now in a larger world, the world of ordered pairs. We can instead first go to the world of ordered pairs on either set and take the union in the world of ordered pairs. Okay, cool. Same business yet again with intersections, same business with set differences. Cool. All right. So let's do a few proofs here. Let's prove a little bit of this. So for part 1, let's go. Well, here, I'll write it like this. For part 1, okay. Suppose that we have something, say, in one of these products. We take some xy in A union B cross C. What we will do now, we'll start on this side of the equation, and we will show that the thing we have obtained also lives here. Does that make sense? That is, we'll show an arbitrary element of the set A union B cross C is itself an element of the set A cross C union B cross C. This shows that this set is contained in the other one. Then we'll do the reverse. And if we have double containments, one thing is contained in the other and the other thing is contained in the first one, they are equal, right? It's one of our most powerful tricks. So from this, we can say by definition, X is in A union B and Y is in C. Okay, nice. Hence, hence, we have two cases. X is in A or X is in B. Notice these need not be exclusive. That is, A and B may contain some of the same elements, right? Nothing too crazy there. Okay. So, if X is in A, then XY is in A cross C. Does that make sense? That is, this is the set of pairs little a, little c, such that A is in big A and C is in big C. Right? If X is in A, then the first thing's in A, and the second thing we already know is in C. Okay, so it's an A cross C. If X is in B, then XY is in B cross C, which again is just the set of little b's and little c's such that B is in big B and C is in big C. In either case, XY is in A cross C union B cross C. So, since we have taken an arbitrary element of A union B cross C and produced something that lives in A cross C union B cross C, we have shown that the first set is contained in the second. So A union B cross C is indeed contained in A cross C union B cross C. All right, here we go. Not so bad. We started out with something in A union B cross C, and we showed that it necessarily belongs to A cross C union B cross C. So we have one containment right there. All right, let's do the reverse direction. Yeah? Okay. I'll write this on the next board to give us plenty of room. Now I'll switch back to another marker to make sure this is easily visible. Ooh, looks like someone was talking about some Kierkegaard on that board. Fun. Okay. Now, for the other direction, suppose now that XY is in A cross C union B cross C. Can you imagine what we might do? Well, then there are two cases. Again, these need not be exclusive. Either XY is in A cross C or XY is in B cross C. Okay. if xy is in A cross C, then by definition, x is in A and y is in C. So x is certainly in A union B as well, and xy is indeed in A union B cross C. Do you agree with that? If x is in A, then x is in A union whatever other set you want. Any set you feel like picking, it would certainly work. Yeah? Okay. Likewise, if x is in B, then x is in A union B as well. So xy would then be in A union B cross C. Hence, A cross B union A cross C is indeed contained in A union B cross C. Therefore, A union B cross C is indeed equal to A cross C union B cross C. And I believe this was by, I don't remember what theorem this is, like 2 point something in this packet. I believe this is theorem, I will find it. Theorem 3.8, yeah. That's by theorem 3.8. All right. That is, if you show one thing is contained in the other and the other thing is contained in the first. I'll write that on this line, actually. Then you have shown that they are equal. All right. The rest of them, the rest of the facts from this whole theorem right over here, can you imagine? They will be effectively almost exactly the same. Yeah? Now, when we do the intersection instead of the union, it becomes easier. Instead of having two cases, either it's in A or it's in B, potentially it could be in both, now you only have the case where it is in both A and in B. Yeah? So obvious modification, hopefully. Hopefully obvious, right? Effectively, you'll do this containment in one way, containment in the other way, modifying only the union now to an intersection, and changing your cases to the easier situation where it's not one or the other, but instead it's just one thing. It has to be in both. The final one with the set minus, well, this says that your thing is in A but not in B, and the second component is in C. So certainly, it'd be the same as taking everything in with first component in A, second component in C, then taking everything with first component in B and second component in C, and just getting rid of those ones from the first thing, leaving you only with things that have first component in A, but not in B, and second component in C. Does that feel okay? You could perhaps prove some things like this if you would like. Yeah? I'm seeing some nods. I'm seeing some general affirmation that this feels tractable or like a tenable prospect. All right. So perhaps I will leave some of those for exercises. The next result is also effectively a lot of the same sort of thing, but it says for any sets A, B, and C, we have the following. 1, A cross B union C is equal to A cross B, union A cross C. 2, so write this up and we'll talk about it. A cross B intersect C is equal to A cross B intersect A cross C. And then finally, A cross B set minus C is equal to A cross B set minus A cross C. That is, we would be remiss since, recall really quickly, A cross B is not equal to B cross A. We would be totally remiss to only give the previous result for unions, intersections, and set minuses in the first slot, right? In the previous one, jumping back to it, I point out that all of our unioning and intersecting and set minusing is going on before the x, before the Cartesian product occurs, right? In the first slot of the two potential things, right? So in the second one, it is effectively the exact same statement, but now everything is in the second slot. And how does it work? The same, right? It works the way you would hope. That is, you can split it up again. Okay, so you have something like a left and a right distributivity. Okay, cool, nice. Now, there is something to be careful of. I will leave the proofs of these as well, since after all, you could just do exactly the same proof, basically, but flip the order of the ordered pairs, yeah? It's the same thing, but just in the second slot now. Okay, however, there's a warning I will give you. Warning. Combining these does not always work how you might naively hope. If you are not careful, you may make statements that are incorrect if you try to combine these things. That is, for instance, I believe it's the same example here. A cross B set minus C cross D is not in general equal to A set minus C cross B set minus D. You may hope that you can somehow double undo these things, right? Where you go like, oh, look, I've got like a set minus over here, right? And so if this is itself a set minus as well, then I can do some more, undoing things, just flip things out, right? Like turn all my set minuses into x's and my x's into set minuses, right? Does that make sense what I'm saying? Yeah? You might be hope that you could do this sort of a trick, but you can't. It does not work. What would be the correct statement? Instead, what ends up happening, well, if we try to say, for instance, use something like this result right here. A cross B set minus C cross D. Well, it looks like this one, but now these are not quite the same, right? Oh, this is a little bit tricky. What would the right statement be?
We keep our B not D. Are we able to keep the B not D, but somehow combine the A and the C?
Ah, I see what you're saying. This is a good one to think on. So if let's say we had this statement right here. Well, this is then equal to A cross B set minus C. Yeah? And so you're saying, what are you thinking?
Somehow the, where you just put the A cross C, your A and your C somehow combine. Or,
Oh, somehow combine. Okay, I think I see what you're saying.
yeah.
Yeah, okay, right on. This is a fun one to think on. I'll let you think on it for a moment. I think actually if you go through and you write out what each of these sets are, this is a great exercise to do. If you are thinking about this, go through, write it out, and see what you get. We'll come back to this either at the end if we have time or at the start of next time. But this is actually a good exercise. This is a good thing to make sure that you fully get it, right? Give it a try. I'll show you an example, though, so you can see that this does not work. So this might also be instructive, but instead of ruining all the fun for you, let's not in the way you might hope, yeah. So is there a good formula you can come up with? A good question. Can you somehow relate those things together? What is the difference? What do you end up missing from one side versus the other? That's a good question. So here, I'll show you an example of how this fails. And maybe when you see the difference, you can get some inspiration for what it should be. Or a way you could write it, I suppose. Not what it should be, that there's some inarguably correct formula. There are many different ways you could write something like this. So here, let's let A be equal to the set 1, 2, 3, those integers. Let B be equal to the set of integers 5 and 6. And let's let C be equal to the set of integers 1 and 2. And D be equal to the integer 6. Then we have A cross B set minus C cross D. Well, let's just write out each one of these. A cross B, take our A, take our B. We'll take 1, 5, 1, 6. Now I'll take 2, 5, 2, 6. And I'll take 3, 5, and 3, 6. That is the set A cross B. Now let's do C cross D. So I'm going to take out 1, 6, and 2, 6. And what do I get left over? Well, I get rid of 1, 6, and 2, 6. That's it. So all I have left is just 1, 5, 2, 5, not 2, 6. That's one of the ones we took out. 3, 5, and 3, 6. Okay. Cool. Does that feel all right? Take this set here and cross out these guys. 1, 6, and 2, 6. So we just go bing, bing. And then you're left with that set, yeah? Okay, on the other hand, A set minus C cross B set minus D. Well, now we take A and we remove C. So we take A, 1, 2, 3, and we remove C, which is just 1 and 2. And we're just left with the set 3. That 3 almost looks like a set bracket, so let me make it very, very, very curly 3. Very clearly not a set bracket. Cross the set B without D. So we take B and we remove D, and we're just left with 5. And hey, this Cartesian product, well, you take something from the first one and something from the second one. There's only one thing you can do that with, right? You get back 3, 5, the ordered pair 3, 5. Whoa, these are not equal to each other. Notice this certainly does live in here, but we've got a few extra things hanging out as well. Uh-oh. What do we think of that? Eh? Maybe? There's something there. All right, so think on it. Let the pieces kind of come together slowly. But, yeah, don't just naively think that you can take something in between two operations and just flop them, right? It is possible to distribute an operation across other operations, but we should not just flop them. Cool? Okay. So if you look right here, think about it real quick. Just take A cross B, set minus C cross D. You could use something like our previous results and perhaps pull some things back. Or we'll go through it together and all the way later. I don't want to just give you enough of a hint that it totally gives everything away. So let's instead continue on to section 3.4 and start talking about collections of sets. Let me laboriously erase this board over here quick, and we'll get going into it. Cartesian products aren't too crazy. They do really work just like the standard xy plane. But the next thing is a little bit more, I don't want to say confusing, but it's a little bit more complicated. We have seen a picture of something like what's going to go on here, but maybe not for a little while. So let me draw a few little pictures of what's happening. Okay, so here is the idea. Oh, other board. Switch the camera. Cartesian products work like the xy plane from high school. That is, you have a set A of things, and you have a set B of things. If you kind of like lined them up, wrote them in a row, then you could grab something from A, and you could grab something from B, and you could kind of like think of it like you're tracing it over, and you get, for each A and B, you get an ordered pair AB. This lives in this kind of product square here, which is A cross B. That is, there's not like any sort of intrinsic actual graph you can draw, right? It's not like there's some obvious way that the things in A should be ordered or the things in B should be ordered. The stuff in a set could be, whatever the heck you want. It could be a little rock you found, like a picture of a train, a number, a whole set of the complex numbers, right? You can have whatever you want in sets. So it's not the case that you can just, automatically produce the same picture if you tried to write out what the product looks like in this sort of a pictorial representation. But if you want to understand what the product is, well, whatever way you happen to choose to line up the things in A and the things in B, if you line them all up, you can just match it up exactly like this. Make a grid, and every place the lines cross, that is something in the Cartesian product. Now, another picture we've seen, maybe you can see some similarities here in some ways, is this business where I said something like, hey, what if we had the set 1, 2, 3? Well, what does it contain? We've got a couple of different subsets. I've got the subset 1, 2. I've got the subset 1, 3. I've got the subset 2, 3. And then I have all the individual one-element subsets. And then I have the set with nothing in it. And you can imagine that you could pretty nicely draw like a little kind of picture like this. And if you look at it, it sort of looks a little bit like a cube, doesn't it? Like take a square and take like another square and you kind of draw the edges together, right? Basically, it's like the same picture from the bottom to the top, right? Yeah? Okay. So you could look at a set and you could think about its subsets, draw this kind of a nice diagram. You add more stuff. You might imagine it just kind of basically adds a dimension to your cube, if you want to think of it like that. Okay, what the heck is this called? Is there a name for this process? Not the diagramming it. This is called like a Haas diagram if you ever are interested in Googling it. But this process of taking a set and thinking about all of its subsets. What the heck is it? We should give a name to that. That seems like a useful thing to talk about, right? Let's give a name to it. Here's the idea. A quick definition. So we are now in section 3.4, collections of sets. Yet again, we are still just exploring how we could take sets, put them together, take a set, get new sets from it. How can we make sets into sets? What kind of operations can we do on them? As many of them as you want, but there are a couple that are pretty distinguished and nice. We've seen Cartesian products, unions, intersections, set minuses, but this thing has been floating around in the background for a long time. What the heck is it? We've drawn this picture a lot. Let's give a name to it. So here's the definition. Let A be any set. The power set of A is the set PA, which is defined to be B's such that B is contained in A. That is, the power set of A is the set of all subsets of A, including the empty set and A itself. So the power set is what we are drawing when we draw this picture. We're including a little bit more information kind of intrinsically. We're also showing like a natural ordering relationship that the power set inherits from containment. That is, you can very easily kind of look at this and say, hey, look, what's the top one? It's the set with the most elements. What's the bottom one? It's the set with the least elements. We've ordered them by number of elements, yeah? So there's a nice kind of ordering hidden in there. But effectively, the thing that takes a set and from it produces all of its subsets, including itself and the empty set, the thing that would take a set and draw this diagram, if you want to think of it like that, then take the resulting sets and throw them in a bag, that operation of making a set containing all the subsets is called the power set operation. So it takes one set and it produces a new set. Cool. All right. So power sets, how do they work? What do they do? Well, one nice thing that they do is they give us information about containment. That is, they preserve some ordering structure. So here's a very basic result that you might find fun to think about as we start working with these guys. For any sets A and B, A is contained in B if and only if the power set of A is contained in the power set of B. That is, containment takes sets to sets, and it does so in a way that preserves the ordering of inclusion. Kind of nice. It doesn't like mess up the ordering. If you've got one thing inside of another thing, then you can like T both sides of it and keep that inclusion. Let's think about what this is saying. This is saying that if every element of A is an element of B, then if you look at all of the subsets of A, well, each one of those possible subsets is also a subset of B. Does this seem reasonable? Okay. let's try to prove it. Proof. First, suppose that A is contained in B. Then, let X be in the power set of A, which, recall, is the set of all B's such that B is contained in A. Or maybe I shouldn't call it B's. Let me call this S's, such that S is contained in A. S for subset. That way it doesn't get messed up with the other B. Okay, so what this says is that S is contained in A. So, X is contained in A, which is contained in B. Hence, X is contained in B. X is contained in A, and A is contained in B. Transitivity of inclusion tells us that X is contained in B. Right? Okay, good. Therefore, X is in the power set of B as well. That is, this is the set of all sets S such that S is contained in B. We've just shown that X is contained in B, so it certainly belongs to this collection. Right? Feel good about that or no? All right about it? Yeah? Okay. Cool. Thus, we've shown that something in the power set of A also belongs to the power set of B. That is, P of A is contained in P of B. Every one of its elements is an element of the other. Okay. Now, we've done one direction. We've said, hey, look, if A is contained in B, then the power set of A is contained in the power set of B. Now, let's start by saying, hey, suppose the power set of A is contained in the power set of B. Now suppose that the power set of A is contained in the power set of B. Okay. What will we do to get back? Then, since A is in the power set of A is in the power set of B as well. So if the power set of A is contained in the power set of B, then the fact that A is always a subset of itself tells us that A is in the power set, and that means that A is in the power set of B. That is, A is a subset of B, since the power set of B is the collection of all subsets of B. Right? Oh, okay, so that direction's way easier. Nice. What do you think? Power sets? Preserve inclusions. Kind of nice. Okay. Doesn't mess anything up there. What other things can you do with power sets? How do they work with our other operations that we've seen? Well, the answer is, for some of them, pretty nicely. Here's another theorem. For any set A and B, theorem, for any sets A and B, the power set of A intersect B is indeed equal to the power set of A intersect the power set of B. Ooh, that's pretty nice. It means that you can break up power sets across intersections. So if you want to take the power set of an intersection, that is the intersection of the power sets. Does that feel all right? Does that seem true? It seems true enough to me, I guess. Yeah. All right. Let's prove it. How would you go about proving this?
of A intersect B first.
Oh, okay, so you pick something in here, and then you show that it lives in there. That's a good idea. Okay. Suppose, let's call it S, is in the power set of A intersect B. Everyone's getting the hang of this showing equality by doing inclusion in both directions, right? Okay, then S is a subset of A intersect B, since A intersect B is itself a subset of, for instance, A. It is also a subset of B, whichever one you prefer. S is a subset of A as well. Hence, S is in the power set of A likewise, since A intersect B is a subset of B, S is contained in B as well. Hence, S is in the power set of B, and S is indeed in the power set of A intersect the power set of B, since it's in both the power set of B and the power set of A. Therefore, the power set of A intersect B is indeed contained in the power set of A intersect the power set of B. All right. So let's do the other direction then. That is, we don't just have an inclusion here, we have a genuine equality. So, in the other direction, suppose now that S is in the power set of A intersect the power set of B. Then S is in the power set of A, and S is in the power set of B. That's what the intersection is, after all, right? It's the stuff that's in both of them. So if it's in the intersection, it must be in both of them, yeah? Okay. Hence, well, for S to be in the power set of A, S must be contained in A, and S must be contained in B to be in the power set of B. The power set of a set is the set of all subsets of that set. Boy, did I say set a lot in that sentence.
It's
Yeah, it's set theory. Set theory, why not? Yeah. But if S is in both A and S is in B, that is, S is contained in A intersect B. So, S is certainly an element of the power set of A intersect B, since the power set of A intersect B is, to recall, the set of all, now I can't use S's, let me call them Q's, why not? Q, such that Q is a subset of A intersect B, right? That is, if S is contained in the intersection of A and B, then S is an element of the power set of A intersect B, which is just the collection of all sets that are contained in A intersect B. You don't really need this last part of this line right here. I'm just trying to make that part of the argument clear. Yeah? Does that feel okay? Thus, we have shown that P of A intersect P of B is contained in the power set of A intersect B. Therefore, P of A intersect P of B is indeed equal to the power set of A intersect B, since we have shown that one is contained in the other and the first is contained in the second. Nice. Power sets. Ooh, You feeling the power of these sets? Very fun. Now, power sets will be like a pretty important kind of foundational piece of what we will do in this class. A lot of the coolest things that we end up doing will be enabled by power sets. Let's think about them for a moment. How many elements are there in a power set? If you have an n-element set, how many elements are in the power set of that set?
2 to the n.
2 to the n. Everyone already knows the answer to this. Okay, well if you didn't know the answer to that, let's kind of think through it really quick as we finish up, since I think we're pretty much at time. I think you can start to see the pattern really quickly once you begin to draw the picture of it. That is, if you go, hey, what's the power set of a 1-element set look like? Well, I've just got the set, and then I've got the empty set under it. Okay, if I've got a 2-element set, then I've got 1, 2 up here. Then I've got 1, then I've got 2. And then I've got the empty set. It looks like a square. All right. This is like I took one of those, put it here, took another one, put it there, and drew lines between it. Now if I have 1, 2, 3, like 1, 2, 1, 3, and 2, 3, and 1, 2, and 3, and empty, if you permit me to do this in this semi-disorganized fashion, notice this looks like a cube. Yet again, it's like I took one of these and moved it slightly ahead and then drew the lines between things, yeah? You can just do this process over and over. Now take another cube, put it next to it, draw lines between it, yeah? Offset it a little tiny bit, and hey, it's the same process over and over. That is, every time you have 2 of the thing from before, right? Here I had this thing, and I doubled it up. Here I had this thing, and I went 1 copy here. So here, if I just kind of like draw like little circles, maybe this will be easier to see. I say, oh look, 1 copy of the square there, 1 copy of the square there, right? If you do the next one, you'll see that I've just taken 1 copy of the cube and I've offset it with another copy of the cube. You get 2 of the thing you had before. So every time you double the number of elements, yeah? So every time you go up by 1, you get 2 things from before. That is, you have 2 to the n things in power set of A when A has n elements. I think the pictures, these diagrams, make it kind of clear how that happens. You're just doubling the number of things every time. Kind of nice, yeah? Okay, fun. I'll see you around next time. We'll start talking about relations. Cool. Have a good one.